Chapter 25, we are looking at the interactions of the nucleus of the atom and what happens when the nucleus decides to change itself up. Chemical reactions involve electrons and trading electrons and manipulating elements without changing their nature. Chemical reactions can either require energy or give off energy, and the nature, again, of the elements do not change, although they may rearrange themselves into new compounds or go from elements to compounds. Nuclear reactions, on the other hand, have a fundamental change in the element. We get a brand new element when we go through nuclear reactions. So it's not just the electrons. In fact, it's really not the electrons at all. It is the nuclear particles, the protons and the neutrons, that undergo changes and create these new elements. Stable nuclei do not go through radioactive decay. So a stable nucleus is one that has the right number of protons, the right number of neutrons, and it doesn't change of its own accord. A radioactive element is an unstable nucleus, and it will go through some sort of decay or change to create something that is hopefully more stable. If you look at a periodic table, what you'll see is the elements are arranged in order of the number of protons they possess. Number of protons, over here on the graph, is atomic number. As you add protons to the nucleus, you change the element to the next element. Turns out that the first 20 elements are very stable, and they essentially have exactly the same number of neutrons, which is on our vertical axis over here, as they do protons. So the ratio of protons to neutrons is pretty much 1-to-1. What this graph shows us is the various isotopes of the elements, their number of neutrons compared to their number of protons, which is why we have multiple dots for one atomic number, because we have different isotopes, and an isotope is an element that varies in its number of neutrons. As we get above element number 20, what we see happening is this band of stability, which goes along here, veers away from the 1-to-1 ratio, and as we get more protons, we need more neutrons. And so this is what statement number 1 says. At low atomic numbers, so low atomic numbers means less than 20, then we have stable isotopes with a 1-to-1 ratio of protons to neutrons. Actually, numerically, it turns out that if I have an even number of protons and neutrons, the isotope is more stable than if I have odd numbers. Not quite sure why that works out, but that's the way it does. If I have isotopes that are above this band of stability, so this one right here, for example, it is unstable. Again, unstable nuclei are radioactive. And so they're going to go through a certain amount of decay so that they can get closer to that band of stability and become stable isotopes. I have other isotopes, for example, perhaps this one right here, that are below the band of stability. They're going to go through decay as well, but they're going to go through a different type of decay to try and approach stability. Now, why do we need more neutrons compared to our protons in the nucleus? Well, if we think about it for a minute, protons have a positive charge, neutrons have a zero charge, and what we'll learn when we get to electrostatics is like charges repel. So we have all these positive particles in an itty-bitty space in the nucleus, and they're going to try and repel each other, which goes counter to the fact that nuclei tend to be stable for most elements, for most isotopes of elements. So what causes them to be stable? Why don't they fly away from each other? Part of it is the neutrons act as buffers. Essentially what they do is they put space between those positive charges. The further away they are, the less effect they have on each other. And that helps to decrease the amount of energy that is necessary to hold those nuclei together. Nuclear reactions are what elements go through if they're unstable, if they're radioactive, and they are attempting to become more stable. So again, if we go back to our couple of options, one of them is if they're above the band of stability, they have too many neutrons. And so what happens is they go through something called beta decay. Beta particles are nuclear particles. They look like they have the same shape, same size, same mass, same charge as electrons that orbit the nucleus, but they are from the nucleus. And so a beta particle will get kicked out of the nucleus because a neutron will decay. And so the reaction looks like this. When we write nuclear reactions, we have to identify both the mass of the particle and the charge of the particle. So our neutron has a mass of 1 and a charge of 0. So mass goes on top, charge goes on the bottom. Our neutron is going to decay and it's going to kick out a beta particle. Our symbol for a beta particle, one symbol that's used is E for electron, because that's essentially what it is. Compared to a neutron an electron has a mass of 0. It's 1,000 times less massive. Electrons have a charge of -1. As with chemical reactions, I have to make sure all my atoms balance in a chemical reaction. I have to make sure my masses balance in a nuclear reaction and my charges. So I have to balance all the numbers on the top. So I have 1 on the left, I have 0 on the right. That means my number for this particle I'm creating has to be a 1 on the top because I have to add it plus the 0 and get a 1 on the left. My charge on the right is 0, and on the right I have to have -1 add to something to get me 0. That something is 1, so I end up with a particle that has a charge of 1, a mass of 1, and that ends up creating a proton. So a beta decay breaks down a neutron, kicks out a beta particle, creates a proton. It also kicks out gamma radiation. So this symbol is gamma and it's radiation. And when you are doing nuclear reactions, that is always present because gamma radiation has no mass and no charge. Many times it is not included in the nuclear reaction. Understand though that it exists. If I don't have enough neutrons, so if my isotope is below this band of stability, so I have too few neutrons, what I have to do is create more neutrons. And so one way that this happens is I go through, or the atom goes through, positron emission, and here I have a proton breaking down and I create a neutron. So we'll start out with a proton, which has a mass of 1 and a charge of 1. It's going to break down, and a positron is perhaps a little bit confusing. We're going to use the symbol of E again because it is the same mass, same size, shape, color as an electron, but it has a positive charge, so it has a mass of 0 and a charge of +1. So I kick out a positron, mass of 0, charge of +1. I'm going to get another particle again. Balance the tops. I have to have something that has a mass of 1. On the bottom, it has to have a charge of 0. So mass of 1, charge of 0, I get a neutron. So positron emission creates a neutron for me. And that gives me another neutron in the course of things that also changes the nature of the element to a new element. An example of positron decay would be phosphorus 30. So the element phosphorus has a mass of 30 and a charge of 15. When it goes through positron emission, the mass doesn't change, so it stays as a mass of 30. I get a positron out of the deal. So 1 plus something has to equal 15. That something is 14. The way I identify what element is, I look on the periodic table and find element 14 is silicon. And so there's my positron emission example again. If I want to put in gamma radiation, there it is. An example of beta decay would be carbon 14 going through nuclear decay. So my symbol is carbon, mass on top is 14, that's my isotope. Carbon has 6 protons, so its charge is 6. When it goes through a beta decay, I'm going to end up with a beta particle, so it has a mass of 0, a charge of -1. My mass doesn't change, so whatever I create has a mass of 14, and the atomic number has to add to -1 to get me 6, so that means this element becomes element number 7. Element number 7 is nitrogen. Again, I'm going to get gamma radiation. So there's an example of beta decay. There's actually another way that I can take care of things if I have too few neutrons, and that's called electron capture. And effectively what the nucleus does is it snags one of the electrons outside of the nucleus that are orbiting it. When it gets really close, sucks it into the nucleus, and it actually combines with a proton and we create a neutron. So electron capture looks like this. I have a proton in my nucleus, and it combines with an electron that gets sucked into the nucleus, and what I get is something with a mass of 1 and a charge of 0, or a neutron. So if I wanted to take a look at an example of electron capture, an isotope that might go through that is argon. Argon 37 has atomic number 18. I add an electron, so this time I have 2 items on the left side, on the reactant side of my reaction. My mass doesn't change, so whatever I'm creating has a mass of 37. 18 and -1 gives me 17. Element number 17 is chlorine. And of course I still get gamma radiation. So there are 2 ways to solve the problem if I don't have enough neutrons, either positron emission or electron capture. If I have too many neutrons, I'm going to go through beta decay.